So, all right, so let's get started. Uh, so, um, so this is our DP0 delegate assembly this week. As I mentioned to those who joined a little bit earlier, Melissa is on vacation this week. Well needed vacation, a well deserved vacation, and she asked me to run today's meeting mainly because I'm also giving the tutorial notebook doing the tutorial notebook this week. So just as a reminder, let's see. We're doing uh, uh, notebook 5, and so I'm the speaker, and we have uh, I've lost I yeah, since I'm on screen full screen, I don't see everyone there, but I know that I see Tina and Greg and and who else from the and who else from the community engagement team. I think Leanne Guy might be by later also. For And there's of course many from DP0.1. You can also provide advice as we move along in today's meeting. So let's see. Let me open up the chat so I can see what's going on here. Oh, okay. So we had welcome Karen. She can't stay long, but you're definitely welcome to come. There are also recordings. There'll be a recording. There's a recording of this session that people can view later. It'll be uploaded hopefully later today, if not early next week. So uh, so let's get started on today. So we have the notebook number 5, and we'll also have after in the second hour we'll have breakouts. Currently we'll have a main room for general Q&A as usual, and we'll have breakout rooms, and we can decide what breakout rooms we want at the end of the tutorial session. So please log into your onto the IDF at data.lcc.cloud. Unlike last time, I think we can just use a medium container in your notebook aspect. It's not doesn't that contain large data sets. And go to your notebooks directory, your tutorial notebooks directory, and you want to open up the notebook 5 tutorial. So so you do want to make sure that you're running a relatively recent version of the notebooks. Uh, so um, so once you go into the notebook aspect, you should uh, you should see and click on one of these on say notebook 5. You should make sure that it was last verified to run at least no earlier than June 27th. But if it is earlier that, then you do need to update the contents of your directory. And There's a few ways of doing this. So actually, let me actually send you the link to this.
I just put it in the chat.
Thank you. Oh, thank you, Tina. Thank you. uh, so if you need to, one way is use the git clone to get a fresh tutorial notebook. You'll want to uh, open up a terminal window by using the plus sign and going to the terminal and opening up the terminal, and then you want to maybe move your current notebook tutorial notebooks into that, or or here, what you can do is you could CD, go to your main directory, do a make dir of my notebooks, CD into that my notebooks directory, and then do a clone of the tutorial notebooks, and then use the panel here to navigate into your updated notebooks directory. If this is only if you, this is again only if you have a version of your notebooks older than June 27th. Another way of doing this is you could just just go to use your browser and go to github.com/Rubin-DP0/tutorial notebooks and find notebook 5 and just save it. Save this INPYNB, this IPYNB file to your computer, to your laptop or desktop, and then back on LSST data.lsst.cloud, you can go and upload that notebook directly into your into your notebook area. Oops, let's see. Just a reminder. Well, we had a bit of a gap in our delegate. We didn't have one a couple weeks ago, but we will have. And this week we're talking about source detection and measurement, and next week we'll have one on data visualization. And you can find out the full schedule of DP0 related things by going to the main DP0.2.lc.io website. And and if you have a question, please use the chat use the raise hand function on your Zoom. And is anyone having any problems? Everything's going okay? All right. Tina, thank you for helping Karen. Okay, so let us now move on to the notebook. So I'll just move this out of the way. And so it's just basically starting completely from scratch. You go to you're at your, and let's make this larger so people can see it more easily on their screens. So you're at data.lsst.cloud, and you want to go to the notebooks aspect. And if you're not previously logged in, you want to log in. And you want to use the recommended release with a medium size of server. And this may take a minute, or hopefully less, if you're not already logged in. And in this case, it's taking maybe about a minute. Okay. All right. Now I think mine is mine might be in a slightly different location than yours, but I think maybe not. I think notebooks, and actually I have various versions of the notebooks I've copied over. Here's I have a nice fresh one here. Oh, I usually like to open up a terminal also, just in case. But today we're looking at notebook 5. Okay, so this deals with source detection and deblending and measurement and object footprints, which are basically, if people are familiar with S extractor, it's sort of like the what do they call it in S extractor? I was going to give you they're basically detection maps and like the detection maps in that S extractor. Uh, so um, So what we'll do is this will we're going to access, display, and manipulate images, detect, blend, and measure sources, and extract, plot, and use object footprints. Now, Greg, who did a quick check on this a couple days ago, realized that this is kind of a this may be more of an intermediate rather than a beginner's, but we'll go slowly. And please ask questions. You have into issues, and it's possible that we might run out of time by the end of the hour. But if so, we'll probably like leave off the end sections about footprints, and that's we might leave that off. It's easy enough to go through on one's own. Um, so we'll be looking at the single epoch images, the so-called PVI or CaliXP images, calibrated images, uh, and their mass planes. I believe we also I ran through this again yesterday. I think we also look at a coad also, or do we? No, maybe not. Maybe not. Sorry, I think it's just single epoch images here. Um, this is a very nice tutorial, which I take no credit for, other than revamping some parts of it for DP0.2 as opposed to DP0.1. So Alex Durga Wagner and Imran Hassan, both long-term members of the Stack Club, devised this nice notebook. There's additional support and documentation at the standard DP0.2 website, and you can also ask questions in the community forum going to this link. So let's see. So this notebook provides an introduction to the pipe, actually running LSD pipeline software, on doing some of the minor steps. It skips over what's called the ISR, or the image. What does ISR stand for? It removes the image. It removes instrumental effects.
Instrument removal.
Oh, thank you, thank you. Yeah, so we start with the calibrated images in this notebook, and people that hires is developed from things out of the data management stack, from Robert Lupton and Michael Wood Basey developed stuff, and of course Imran developed this for the Stack Club, and so it makes use of a couple of these algorithms, the LSD.mes algorithm method, and and if we get to it, we'll look at the footprint of individual detected sources, and of course we've used before, we use the Butler, and we'll look at these calibrated single epoch images, and we'll also display image cutouts. I won't go into gross detail over the imports, other than we use some of the standard packages, plus some additional ones that are particularly for the pipeline. So we're all familiar with like the matplotlib, and there's some special matplotlib special toolkits that we also make use of in this notebook. And then there's various things the pipe from the LST data management science pipeline, and in addition, and the packages, and also particular tasks, particularly the characterize image. We'll want to do a characterization of an image, like the measure the PSF and things like that, before going into the source detection. And then often, especially in crowded fields, but not necessarily in crowded fields, also you'll often have sources that are overlapping, so we'll need to deblend those sources, and then we'll, after deblending, we'll want to measure those. We'll make use of the single frame measurement task for that. So let's see. Uh, okay, so remember to run a cell, use Shift Return. Oops, sorry, I'm all the way at the beginning. Okay, so okay, and the asterisk means it's going through the process. Okay, it's finished. Uh, there's some warnings which will be disappear in future versions of um, of the notebooks. But but that but no need to worry, no real worry to worry about this at this time. Just note that these will disappear in the future. Uh, then we also want to define some functions. In particular, this is very nice for we want to make use of and for like publication purposes or display purposes for others. It's nice to make use of a color map, which is accessible for the colorblind. So we kind of in Rubin we kind of try to aim to make use of these particular tableaus or color maps that are accessible to also to the colorblind. Uh, and then we just define some standard we want to make we want to adjust the size of our figures for later on in plotlet. So we change we change the default plot some of the plotlet parameters for the figure size. Okay, next, we want to access the data. So we'll use the butler, and we'll use it to access a particular a calibrated single epoch image from the DP0.2 data set. So we need to know its data ID, which is actually the visit, the visit number, the visit ID, and the detector number. The visit defines when a given exposure was taken uh, by the LSST camera, and the detector, there's 189 detectors or CCDs on that camera. So you need to say, and we want to look at one particular CCD detector image. So so for the butler, we want to define the configuration, which is a large data set of data, and we want to look at a particular collection within that data. And so we want to look at the DP0 configuration and the collection that were and the collect and this and the D2.2i slash runs DP0.2 collection. And this generally this is what you'll typically be using throughout for DP0.2 data work in these assemblies. In particular, we'll look at detector 75 in visit 512055. So we define a data ID using a Python dictionary. So we use a visit. So we define that data ID, and then we use the butler to grab that Kali XP for that data ID, and so we run that. Okay, I'm going to just make a brief stop. Are there any questions at this point? Any issues or any difficulties? All right, don't see anything. Okay, so let's move on. So a Calyx is not just an image, not just the raw image data. It also contains mask planes and also a variance map, which are useful for processing later on. And so here we can take a look at some of these things. So here we just so basically this will output numpy Python numpy arrays. So you can uncomment out, say, the content. See, look at the contents of the mask image, and you'll get uh, the you'll get the pixel values, actually, you'll get the mask, and you'll get mask values. You'll also get information, and for the mask, so you have a mask plane that has uh, things that are masked as bad pixel or cosmic ray or the pixel is affected by crosstalk, whether there's a detection in there, or whether there's what's called a negative detection, or you get a negative values, whether the object's near the edge, or if there's an interpolate, or if the pixel was interpolated over due to I don't know bad pixels or something like that. Uh, whether this is part of the non a non-blended whether this pixel is in a non is within a blended or non-blended object, or it's whether there's no data for this pixel, whether this is a saturated pixel, or there's some suspects, there's something else suspicious about it, or if it's or if there's a not, or if there's a non-number in that, a nan in that pixel, and it's not hasn't been masked, and then you also get the variance values in basically data numbers, and you can actually you can also look more in more detail at say that was the full mask, the image plus mask, but you can also break that apart and look at say just the the pixel values, the image values, or uh, just the mask values. And these are bitwise masks, so you have to it combines so you can have multiple so you can have things that are combinations of these binary bitwise masks. And we'll see a little bit later how to deal with those. And then basically the variance per pixel. And so you can also just there's also a alias to just using callops, so you don't necessarily need to put mask image dot image, but you can also do callops dot image or callops dot mask, and so on in this case. There's also additional information in addition to those things. There's in the header information. There's the PSF for that the average PSF for that image. It's in a PSF form though, so a little harder to look at. There's the WCS or the coordinate information, the sky origin, the origin in ARIAN deck of the origin of the 00 point for that, or actually the in this case the ARIAN deck and its complementary pixel x and y pixel value for that coordinate for that origin of the, and you also get the pixel scale of it's about zero point 0.2 arc seconds per pixel. Okay, since we want to do our, so these actually have all their source detection already done. We want to actually do our own source detection. So we want to actually we want to unset. Remember up here we had, oh, sorry, let me just unmask this briefly again. Uh, uh, Remember in the mask, it said whether an object was detected or not, whether there's an object detection within that pixel or not, whether that pixel was part of an object that was detected or not. We want to unset that and redo the object detection. So we can unset the bitwise mask for in the mask plane for that detect. Basically, unset this mask bit for that whole image. And then, okay, then we can just take a look at our image using the standard AFW display that we've seen in previous tutorials, and we'll use an hyperbolic arc sine scaling with using the z scale parameters, z scale scaling. And voila, we have an image with stars and galaxies in it. All right. I'll make a quick stop here. Any questions or comments or difficulties? All right. Okay, let's move. Let's continue on. And of course, if you have questions, you can add them to add them to the chat. Okay. So these Kali XP images, they've been background subtracted. They basically the sky and other background has basically been well, basically the sky background has been fit and removed from this image. So it's basically the sky background is a constant zero throughout this image. Why don't we add it? This is actually not strictly necessary for object detection, but why don't we add the original sky background in, and we can subtract it and let the processes subtract it back, refit it and remove it later. So we can add that back in, but first we need to grab it. So that is also in the butler. So we can use for that same data ID for that same CC that same visit number and CC number. We can grab the background that was fit and removed, and we can take a quick look at. We can just do this similar. Let's do a plot and see what that looked like. So it was basically fit by a localized polynomial. You see there's a little bit of a gradient. It's not a huge gradient. It's only like about 6 data numbers from low to high. So you don't really see it in the you don't really see it. So you don't really see it when we add it back in because the numbers here are a few hundred, so it won't be obvious. But we'll add that back in. Uh, And we want to note that you just want to run this once, otherwise you'll keep on adding that background image over and over again. And we just want to add it in once, and then we can plot it again. And you'll note visually it looks a lot like the previous image. It's really hard to see any gradient in there, but it is in there. One thing you will notice is that this the color scale is now no longer values of a few hundred, but now of a few thousand, because it has this about 3,800 data numbers added to each pixel from that sky background. So you're looking at roughly well, not entirely, but partially uncorrected Kali XP file here. Not quite what you get from this guy because there's also flat fielding and so on, which we're not worrying about at this point. Oh, okay. So now, so I'll make another brief stop because we're about to get into the meat of this. Everyone is caught up. Any problems? Any issues? All right, let's continue. Okay, we're going to use the data LC data management science pipelines source detection, the blending and measurement tasks. Uh, I mean, we're mostly focused on detection of sources, but you have to do some of these other things also to get a good source detection. So we imported these tasks above when we did all the imports at the beginning at almost the first cell that maybe the first cell that we ran earlier. You can learn more about these different things if you go to this link here, pipelines.lsst.io. And you can see lots and lots of information. uh, but it's all there. But what we'll do here is first we want to create a format or a schema for the table of objects that we want to that we want to detect. That we hope all our detections will go into this source table or detection table, and we want to set up a an initial empty table which has the forms of the format that you want later on. And more or less, it's going to be at first it's going to be a ID, an object ID or a source ID, and an array and deck. Actually, I'm going to comment this second part out for a second and run this. And so yeah, we use this minimal schema and it creates a name or it creates a table, an empty table with an ID and RA and a deck. Oh, it also includes whether this object is a when you do the deblending, whether it's the parent of children objects, which you so you have a if you have a parent object which has multiple objects in it, and you deblend it, the deblended objects are children, and the topmost object is the original point is a parent. All right, so okay, we create the schema. We don't need to print that out, but we need to do that. And so and then we'll add in additional information. Let's see. Oh, no, wait, no, we don't adding the additional information here. Basically, here we're just uh, creating a container which will be used for that schema. And then next, we will configure the different tasks, the different detection. Well, first image measurement, image characterization, detection, and deblending tasks. So, okay, do I want to? Okay, I will briefly uncomment this out for the characterize image task for the config class within that. What the configuration class for that? It's long in detail, but it has all the information you'd want there. Say how many when you're calculating the PSF, how many iterations you want to do, uh, and initial estimates for the background, whether you want to do deblending or aperture corrections, and all sorts of things. We'll just do a fairly simple process. So let's see. We'll set some basic parameters here. So first of all, let's see. So we'll do something very very basic. We'll do for the for the for characterizing the image. We'll just set the PSF iterations to a single iteration. For source detection, we'll do a threshold of 10 sigma. So here we define the value and the type. So it's the value is 10 and the type of threshold is a standard deviation. So 10 standard deviations. So we're doing a 10 sigma detections. Um, and then and for the deblend, we will feed in the schema information into the source deblend task, uh, and actually through all the actually also for the source detection also we also get not only configuration but we also give the schema for the initial schema, and this will actually add in other parts beyond just the ID, the RA and deck, and whether it's a parent or not. Each of these tasks add in additional rows, additional columns into the schema, and then uh, we'll after we do the deblending, then we'll do measurements on those, and we'll add in the schema, this the configuration file, and this container information. So we basically just want to run. So we run this. Oh, I ran the. Okay, we run this, and it just basically sets up the configuration. If there's a warning here, if you want to change something, you don't want to change it on a you don't want to just change it in a different. You don't want to just ad hoc just do of a config threshold equals or let's see config.ps iteration something else. You want to actually redo the whole characterize reset the configuration entirely. You don't want to just set the value, but rerun the task this task for setting the configuration as we show here. And as mentioned before, there's you get information on these tasks by doing using the usual help routines. And okay, so now with all these configurations configured, we can actually create the table based upon that schema, which is built up by our first instantiation, and then by running these configuration tasks. So now we have a table. I think it will be. Let's see. I'm going to add something. I don't think print's going to really show too much, but it's interesting to take a quick look. No, it shows the table. Let's see. Can we do a tab dot? No, we don't want to do any of these things. I guess we do that maybe. Oh yeah. So here we can see what the final scheme will be, or the final table columns will be. Nothing's been detected yet. This is just an empty table. So you have the ID, the ARIA deck, parent, whether it's if it's a parent, whether it's how many children were deblended from that parent object, various flags, basically lots of useful information, including the instrumental flux, blendedness, yeah, basically lots and lots of information. Many of which may end up being just nans, not a numbers, but if for especially for like really faint objects which are not too well characterized. Okay, before we actually do any detection, we need to characterize that CCD image. Before we do that, I'm going to make one brief stop. Any questions or comments? Any problems? All right, let's move on. So now we will run the image characterization task, and then we'll take a look at the PSF at our point. It'll kind of do a mapping over it'll fit over the field of view, and you can get the PSF at a given position after fitting objects to a PSF, and you have the PSF is allowed to vary over the CCD, and we get a fit. It's modeled, and we can find what the PSF is at a given point. So first we run the characterize image task. We run that on that image, and then we'll look at a particular pixel. Oh, and this double slash, that's a Python operator for its division, but it's a ceiling, no, floor division. It basically removes the float part of it. It just returns an int. So we'll run that. Define a point we'll choose a particular point in the image, we will define that using the geometry point 2D function, and then we'll grab the Kali XP, and then we'll grab the PSF at that point and see what it is. And it will, this will take a few seconds to run. It identifies objects and removes, subtracts the back, it fits and subtracts the background and measures the PSF, finds, identifies useful stars for that. Uh, and and then it does a fit on the stars that it finds as good PSF sources. And this takes I don't know, 3 seconds or so. Everyone keeping up? Any problems? All right.
I'm good.
Okay, sounds good. Thanks. Let's see. It's still churning away. Okay, maybe it takes a minute. Or maybe we're all writing this at the same time. Oh, no, here it goes. Okay, so it churns away, and our value is sub-arc second seeing, 0.97 arc seconds for that, which of course was what we expect for LSST, is something sub-arc second. Actually, this is maybe not the best for LSST, but 0.987 arc seconds. Now that we've characterized the image and we've fit the PSF in it, we've fit fit a model for the PSF across the CCD. We can now run the source detection. Um, using the parameters that we defined before. So we'll uh, run this using the source detection task on the CalXP, and have the results go into our table. All right, so it found 940 positive peaks uh, in uh, in 888 potential objects. Um, and using a 10 sigma detection threshold. Um, and then to look at, and it returns what's called it returns a struct, which is a container for storing multiple components. And we kind of need to iterate through those to take a look at what's in there. So we can do this using this cell here. So we'll iterate through the items in the result that was returned above, and see what's in there.
There's a quick question in chat.
Oh, okay. Oh, okay. Um, no, well, I believe it is. So the question is, do we assume the PSF is axisymmetric and constant throughout the Kali XP? And I believe that, I mean, I could be wrong if there's anyone from data management on, they should definitely correct me. But I believe they fit for. Uh, um, I mean, they definitely fit for a varying PSF across the Kali XP. Axisymmetric, I I'm not 100% sure there. I think uh, I'll just say I'm not sure. We might need to ask someone in data management about that. So uh, no idea. Sorry about that, Bob. We'll try to get back to that later. Okay. Okay, let's move on. So so things so we get various here are some of the results we get out of the initial detection. How many positive peaks we have, how many negative peaks we have. Oh, I don't know, recall what the factor stands for. I believe the positive threshold is basically our 10 sigma of what background there is, number of positions, number of peak positions, and likewise for negative detections. And we can take a look at the number of, we can take a look at how many positive peaks were detected, and we find there were 940. If we wanted to actually go back and rerun with like a lower threshold, we got a whole lot more, a whole lot more positive peaks detected. Whereas a lot of those may, as you reduce the threshold over, some of those may be false detections. Just, but but yeah, if you want to look at lower thresholds, you can always adjust that. Now, when I first ran this, when I was testing this for DP0.2, I ran an issue that I was not getting these values. That I changed it. And apparently, if you get but that was because I was using a different user of the data management stack, the code, and so these can vary slightly as they develop as the data management code changes. If you use a different version of the science pipelines, uh, the algorithms beneath all this, you may get slightly different values. If you come back to this a year from now and run this, you may get slightly different numbers. Let's see. We can look at this the sources. Actually, didn't tell us too much. What was that? Okay, let's just just okay, let's see. Oh, so here we can see that we can take a look at the sources. We get the ID, the RA index, all those things that were in our schema. Uh, all these end up being uh, NANs. Uh, I'm not entirely sure why right offhand. Uh, but and if you wanted to, you can save one of these. You can save save these to save that table to a fits table, and you can save your image to a fits image. Uh, we won't do that here, but if you want to, well, okay, I will. Okay, I will. I'll just do that. It takes a second. You run that, and you will notice it will. Uh, okay, it's taking a. Oh yeah, Here's one that's popped out, and it's taking a few seconds, but it pops up out in your directory here. You might want to move it later or whatever. Okay, let's now let's deblend and measure these sources, and we only have about 10 minutes left in this hour, so I'll try to pick up the pace a little bit. Uh, so we'll just run the source deblend task, which will break up apart the things which are the blended sources into individual childs. The parent blended sources into their individual child sources, and then measure all those child sources. Uh, and so it's turning away. And it's done. And okay, before we looked at um, this is just a uh, a basic print to screen of the result, but we could actually create a look at it as an AstroPy table, which is a little bit prettier. So you get the current RA and the current deck, whether it's a parent, if it's a parent, how many children there are, uh, all sorts of deblending stuff, and there's a whole lot of columns here. The RA, the centroid the weighted centroid for the in X and Y, the errors, uh, various flags, uh, lots of flags. Oh, let's see. Blendedness. Fluxes. Uh, of blendedness values, and basically many columns of data. Okay, and now as let's see, any quick questions? Okay, let's move on and let's plot these onto the image. So so we can go back. So we'll use we'll do a cutout using AFW display. We won't look at the full Kali XP image, but we'll define a bounding box, um, and um, and do a cutout and just look and then display that cutout and overplot some of these points on that cutout. So here, this box kind of defines how you might create a cutout uh, uh, for uh, for an image, and then we'll display that. And so here's a zoomed in point of the image, and each of the objects are encircled with a little red dot with an orange circle around each of these objects. All right. Any questions or comments? Everyone's caught up, more or less. All right. Okay. So it looks like we will have a chance to go through a very quick. Looks like we can make it through the footprints. So yeah, that's what the word I was looking for. Don't do that. That was the word I was looking for before. S extractor segmentation map. And so these what we call footprints here are more or less similar to what an S extractor segmentation map would look like, is where it basically maps out what pixels are associated with which detected object. Uh, so, uh, uh, so, um, so yeah, just to quote Bosch et al., footprints record the exact above threshold detection region on a CCD. These are similar to S extractor's segmentation map in that they identify which pixels belong to which detected objects. Uh, so, uh, uh, so the source detection task actually stores the footprints associated with the object, so we can actually go back and take a look. So we can grab the above threshold footprints that were detected, and in this case, we'll set them to assign them to the variable FPS for footprints, and then we can get a rough view. Basically, this is a 2D NumPy array, more or less, to look at uh, the footprint for the zeroth, basically first object, the zeroth object in that list, in that table. And so, yeah, so you can sort of like a picture if this were like on an image. So you have zeros are where there's nothing, and ones are where is where the is where there's a pixel that has that which is above the threshold. So you do see sort of a circular-ish area in the middle for this object, but not quite entirely symmetric, as we'll see a little bit later why. Oh, and also this is kind of opposed to an image. This is flipped. It would be upside down relative to what you'd see in an image. We'll see. We'll take a look. We'll take a quick look using heavy footprints. So, so our footprints indicate which pixels they consist of, but not the values of those pixels from the image. So we're going to extract these values. We want to convert our footprint into a heavy footprint, basically mapping the footprint to the image plane stuff. So we map the footprint to the object image. So first we see, okay, it's not this is what we did before. That's not a heavy footprint. Now we make it heavy by matching it to this to do the mapping against the mask the image and mask the masked image, and we'll call this the heavy footprint, heavy footprints. And then let's see, we can take a look at this array. It's very long. It has all the other information. It has all the other additional information in it. Image value, pixel values, masks, and so on. So we'll kind of ignore that for now. Now let's see. Okay, so now we can do a plot. And with the plot we use the span. We use the span, and we reassemble it into an image. And I won't go into the details because we only have a couple minutes left. But basically, this cell will do that magic, and voila, you have here's the object. You see it. It's not symmetric, and it's flipped compared to what we saw before. Here's the spot where we had fewer ones, or there's a lot one that has looked like it was at an edge or something, which in fact actually it is. This is actually an edge object, which we'll see with this final thing. We'll look at the 1D mask array for this heavy footprint. And okay, so this is just for that one particular, the footprint for that zeroth object, that first object, or the first object in that table. And you see the masks have different values. So there's a bunch, which actually indicates that some of these have the edge bit flipped on. This is near the edge, and we can take a little bit closer look here. We can grab the, we can, recall that the edge is 4. Let's see. So what do we have here? So this is a bit mass, and so these are like 2 to the, so edge is 2 to the 5. That's 32, and so and detected is 5. That's 2 to the 5 plus 2 to the 4. So things which are detected and near the edge, those will have values of 48, which we see we have a bunch of values at 48. This is still a 1D array, so we want to take a look at what that looks like on an image. So we can basically redo this image, but now we can color code by their bit mask, which we will do here. I won't explain this in detail. I'll just say, just point out this is the magic that will get the job done. And so yeah, we see that there's things with the at 48. That's indicated it's near the edge, and a good chunk of that is near the edge, and actually some of it is actually off the edge. And that is our tutorial on some basic image characterization and source detection and deblending and measurement. Do you have any questions or comments?
Nice
All right.
work.
Oh, thank you. Um,
Doug,
all
I
right.
have a quick question. What would you use the heavy footprints for specifically? What are the applications there?
Well, I think the basic footprint just gives you whether you are basically just gives you whether you're whether there is a object detection there, whether a given pixel is in an object. The heavy footprints allow you to connect that information to the additional information for those pixel for that given pixel. Say pixel 375 comma 480 has a footprint value of 1, which indicates that it's part of an object. You can then, with a heavy footprint, that allows you to go from, okay, this pixel, that allows you to easily look at the mask values or pixel values and variance values for that pixel associated with that object in that footprint. So basically, it's basically a connector to the rest of the data for that pixel.
Okay, thanks.
Okay. All right. Let's see. I'll stop sharing screen here. And oops, let me go back. I think so. That's basically the end of the first hour. And let's see, where did so let's see. Let's actually, I'm not sure. Can I make breakouts, or Greg, do you have to do that?
I have to do this, but the question is, so who is interested in actually joining in into some kind of breakout room? Go ahead, raise your hand and tell us that you'd like to join some other folk in a specific breakout room.
All right, so we'll leave the main room for the general Q&A. In the past, we've had people looking at variability in transients or large-scale structure or synthetic source injection. Do any of those interest anyone today?
Just go ahead, let us know in a chat window.
All right. Well, I guess we could just, if there's no interest at the moment for a breakout, we can uh, 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 for the time being, keep the just the main room open. Greg, do you need to leave?
Not today. I made sure that I do not have to leave today. Let me set up 3 breakout rooms, and if you decide to, we're gonna just call them room 1, room 2, room 3, and you can just go off and maybe work on your own. So let me just start with that. Is that okay, Doug?
That sounds great. Yeah.
Okay, so there will be just 3 rooms, and then I can potentially rename them at some later time. Or of course, if you want to do things on your own, you can go back to notebook 5 and just try to rerun the whole thing. And if there's anything that is not clear, Doug and I will be here on the in the main room and can answer your questions.
All right. Since it's actually a really small group, I'm gonna I think, and since we're all kind of for the moment staying in the main room, I think I'll pull a Stack Club feature and maybe ask each of you what you hope to do today, if you're planning on staying on for the next hour, and I'll put Bob on the spot. Bob, what are you gonna? Since I know you have since I know you have a clear idea what you're gonna do.
Well, I got a regression code that I've been writing for analyzing magnitudes. I got it working yesterday, so so my life is complete. But I thought I'd continue with that, and I want to work on shapes. There's so many different types of shapes. I want to look at them and look at correlations and just get better at scalar and regression.
All right, sounds good. All right. Okay, I'll go next. No, actually, I won't go next because I don't know what I'm going to do. Let's see. I don't know. Greg, are you planning to do anything
I actually
on the?
started to play around a little bit. Well, this is sort of my science topic that I want to start pursuing a little bit more extensively. At some point, we're going to start looking at some of the sources that are gravitational lensed. And
Oh,
I'm sort of working out, needless to say, this is really useful because you can actually measure the presumably time delays between two spectral, temporal features of quasars, and that if you can get the somehow the shape of the mass sheet that is
mm.
lensing, you can actually determine Hubble constant, presumably, or at
Oh
least
yeah.
some constraints on it. So I started to think a lot about that, and I'm actually now trying to understand what are the errors in the autocorrelation function if you actually do not have two separate images, but if the images are blended with each other. So I'm
Okay.
thinking about this sort of,
Oh
as
wow. Oh, that's
yeah,
cool. Okay, that's
it is
great.
pretty cool. I'm just trying to understand, what are the specific details of the statistic of the autocorrelation function. So, it's a project that I've been thinking about for the last few weeks already. So it's a perfect time for me when I'm not doing anything else. So
Oh, that's great. That's great. Okay,
yes,
that sounds great.
it's a
Thanks.
cute little project.
All
Again,
right.
Rubin hopefully will have a lot of gravitational lensed uh, images, and in some cases they will be deblended completely, separate. In some cases they will not be.
All right. Yep. All right. That sounds great.
Yeah.
Will
Okay.
you report back to us sometime?
Well, this is something that I probably, before I report to you and confuse you, I want to maybe bounce it off some of our local statistics experts. We are
Okay.
lucky that Jeff Scargill is of the long
Oh,
story
okay.
periodogram. He's actually working quite closely with us in Stanford.
Okay.
He retired now from NASA Ames, so I'm
Okay.
going to work with him a little bit. But yeah, I hope to eventually come up with something that can maybe even become a notebook. And independently of that, I'm also, as you know, I'm also working a bit with the Rubin Science Platforms, the other instance, not the notebook, but
The portal.
the
The
portal. That's
portal.
right.
Yeah.
Yeah, and I'm trying to figure out, if I can do any of the sort of interesting demonstrations that would be essentially equivalent between portal and notebook.
Oh yeah. Yeah. Oh yeah.
Anyways, that was maybe too long of an explanation
Oh
of what.
no, that's great. That's great. Okay. Let's see. Let's see who else will I pick next. How about Alan? Alan, what do you plan on working on today? Or Alan, are you still there? Maybe not. We'll come back to Alan. Uh, uh, let's see. John Carlos, would you like to say a couple words about what you hope to do today? John Carlos? Okay. Yeah, it is after the first hour, so I think a lot of people are taking a short break. I would too if I weren't speaking. How about Ryan? Ryan, what are you up to?
Yeah, so I think since I'm relatively new to joining these sessions, I'm just kind of listening in and catching up with how these kind of go.
Okay, that's great. Yeah, actually, I myself, I think I might look at some of the later notebooks, which I haven't looked at recently, or the portal. I'm pretty far. I need to remind myself of all the nifty things in the portal. But yeah, yeah, sounds good. All right.
Yeah, the transient stuff you mentioned sounded kind of interesting too. You're saying like source injection or something, or
Oh yeah, there's both. Yeah, there's different groups that were looking at adding sources into the images and then trying to redetect them. There's a couple different people who are looking at that. I know Matt Wiesner does that. There's a who else? I think was Jeff doing some of that. I
I think
think.
Jeff was, yeah, that's right.
Yeah, yeah. Yeah, just at a Delve collaboration meeting today. Uh, so unfortunately he's not with us, but he's here. He's here almost every Stack Club and Delegate Assembly.
Mm.
And I think he was also looking at he made a nice notebook on looking at variability and transients that he showed off a few weeks ago. It was really nice.
These are the '07 notebooks.
I don't remember. I'm not sure. It may have been something he was doing on separately, not as a necessarily as a tutorial notebook, but as
Oh,
a
okay.
I'm not 100% sure.
If I remember correctly, that particular notebook was actually periodogram of some kind of a variable star, periodically variable star.
Yeah.
It actually illustrated the fact that you can actually implement the periodogram and actually get the correct period. So that was really cool.
Yeah, it was really
Cool.
nice.
Okay, yeah, I should catch up with him on that then. That sounds sounds pretty
Yeah,
cool.
I mean, he's here Friday, almost nearly every week. But yeah, this
Right.
week he's at a meeting. Uh, let's see. Tracy, would you like to share what you're up to? Okay, come back. Tina, how about you?
I have not decided what I'm going to do today.
Okay, that sounds
Yeah,
good.
sorry.
Options are open. Yeah, same.
There you
Yeah,
go.
same with me.
The world is my oyster.
Yes. Okay. Christina, how about you?
Oh, sorry, I'm muted. Hi.
Oh, it's no problem.
Um, sorry, can you repeat the question?
Oh yeah, just going. I was just taking a note from the Stack Club and just thought we'd go around since there's not so many of us, just go around the room and ask what people are planning to do with this. Now 45 minutes of
Oh.
the second hour.
Yeah, so I was just gonna sort of keep messing around with my draft notebook about the image cutout service that we talked about yesterday.
Okay. Oh, that's great. Okay,
Yeah.
good. All right. All right. Let's see. I think most everyone else. Uh, let's see if any. I think I caught everyone. I went around. Some people were taking a short break, but does anyone else would like to share what they like what they're planning to do the next for the second hour or 44 minutes? All right. Okay. Well, I guess if you need a breakout room, Greg has created 3 of them. Otherwise, um, uh, um, I guess we'll just stay here, stay in the main room, and maybe we'll just have just do a quick meetup at maybe 55 after the hour or 5 minutes before the hour, uh, and see how things are going.
I
Oh,
believe,
Vittorio. It looks like Vittorio. Mr. Tom. Okay, he left. Okay. Oh, sorry.
no, I was going to say, I think we can stop recording now. Greg, I don't know.
Oh, yeah. Yeah.
I'll do
Okay.
it. Yeah, we can